Okay, we will now do some solved problems on the kinetic theory of gases. So we'll begin with the example here. It says 1 mole of an ideal gas at STP has a volume of 22.4 times 10 to the power minus 3 cm cube. Sorry, this should be cm cube, not sorry, this should be meter cube. It's not d. Remove that d. The d is not supposed to be there. It should be meter cube. There shouldn't be any d there. At 273 Kelvin, calculate the pressure of the gas. So here, let's talk about standard temperature and pressure. The standard temperature and pressure, which is noted by STP, refer to the temperature of, you have 0 degrees Celsius or 32 degree Fahrenheit or 273 Kelvin. So using the lower fixed point of water, the lower fixed point, the 0 degrees Celsius or 32 degree Fahrenheit or in Kelvin 273 Kelvin. So that's for temperature. Then for pressure is 1 atmosphere. 1 atmosphere is used for pressure. Then the example we are giving now, we will now refer to our ideal gas equation, which says that PV equals nRT, where the number of moles n, the small letter n, which is the number of moles. You can see this is the same question, I just copied it down here. So you use the formula PV equals nRT. N is 1. N is 1 because you are told that it is a 1 mole of gas. 1 mole. So we are asked to calculate the pressure. Let's know what the pressure is at standard temperature. So the formula we have there, PV equals nRT. You make P the source of formula. P equals nRT over V. So N is 1. R, gas constant, is 8.31. T, standard temperature, is 273 Kelvin. Divided by what? nRT divided by the volume. So the volume V is this, which is the volume given to you. So when you do that, you get this value for your standard pressure. Alright, so that's just a simple example there. We will also consider the other examples. We have this particular example that is a bit trickish. It says that a gas contained in a cylinder of volume 1 times 10 to the power minus 2 meter cube. This should be meter cube, not meter squared. At temperature 322 Kelvin, 325 Kelvin, and pressure, when some of the gas is used at constant temperature, the pressure falls to this. Now calculate the number of moles used. So now from the ideal gas equation, PV equals nRT. Now we have two cases. Now we have number of moles that differ. So in the first case, the number of moles N1 equals P1V over RT. Here we're considering the volume of the gas, the cylinder. Okay, the volume of the cylinder V. It is the same. The volume of the cylinder is the same. It's just that the pressure fluctuates. Pressure and number of moles are the things that change. So from the ideal gas equation, you make number of moles source of formula. N is going to be PV over RT. So you now calculate N1. You solve for N1 and also solve for N2. Okay, this is for N1 and then for N2. N1 is P1V over. So number of moles used is the difference between the moles N1 minus N2. And you subtract the second equation from the first. You have that. So factoring out V that is common, you have P1 minus P2 bracket V times divided by RT, and then you substitute their values. P1 is 2.7 times 10 raised by 5, and here is P2. Here is the volume, 1 times 10 raised by minus 2. The gas constant R is 8.3, while the temperature, absolute temperature given, is 325. So simplifying this gives 0.5 C. So the number of moles of gas used is that. Then the next question, the next example there is uh, calculate the gas constant per unit mass of hydrogen at STP. The density of hydrogen is 0.09 kilogram per meter cube. So we are looking for the what? The gas constant per unit mass. It's not just gas constant, but gas constant divided by molar mass. So we'll solve the ideal gas equation, whereby we'll have the formula such that the gas constant per unit mass becomes the subject of the formula. Okay, now we're going to use the formula for that relates total mass and molar mass. So total mass of a gas is the number of moles multiplied by the molar mass. So molar mass is the mass of 1 mole of a gas. So if you multiply the mass of 1 mole to the number of moles, you will get the total mass of gas. And then number of moles from this formula, number of moles will be total mass divided by mass of 1 mole, that is the molar mass. Now the ideal gas equation is PV equals nRT. Now you substitute total mass over molar mass for N. For N, you substitute total mass over molar mass times RT. So it means that PV here equals M total over capital M times RT. So now if you take V to the other side, to the right hand side, P will be molar mass, total mass over V multiplied by RT over M. So now m total over v is the density. Density is mass over volume, so total mass over volume. So that means m total over v is now replaced by rho. Rho is the symbol for density. And then when you do that, our formula becomes P equals R over capital M times density times temperature. So this R over M is the gas constant per molar mass. So this gas constant per molar mass will now make it the subject of formula, because that's what you're asked to calculate. Making a subject formula, you will now have pressure divided by density times temperature. These are the values given. Pressure is given as this because you're told it is 1 atm. Calculate the gas constant per unit mass of hydrogen if at STP the density of hydrogen is this. So the pressure of a gas at standard atmospheric temperature and pressure is this. So if 760 millimeters of mercury, you know that this pressure is from our, I think from our former derivations, density, height times density times acceleration due to gravity. So that when you now slot in this to density and then the acceleration due to gravity, this is what you have for pressure. Or you can just use the formula, the value for it. All these 760 0.7 times this is just the value we got here for pressure. If you multiply those things out, this is what you get. So if you cannot remember those stuff, you can just use this value for standard pressure, 1.01 times 10 raised by 5. All these things, all these products, they give you that. So the gas constant per unit mass is pressure divided by density times temperature. Now we have pressure, we have seen pressure. Now the density, we are giving density as 0.09, and then we are giving temperature as the standard temperature, so the absolute temperature. So when you now simplify, the gas constant per unit mass is this. So the fourth example there, determine the universal gas constant R if density of oxygen at STP equals 1.43 kilogram per meter cube and molar mass of oxygen is 32 times 10 to the power minus 3 kilogram per mole. And then we take the pressure at the standard pressure, that is, which is 1 atmosphere. This value, remember I just told you that this value 1.01 times 10 to the power 5 is still the same value you get when you do this calculation here, 0.76 times this, blah blah blah. So you can easily memorize this so that you always, you don't know if you ask question, you need to use the value, you'll be able to get it right. So now when we are asked to calculate the gas constant from equation 13, that's the equation we have used so far in our lecture, we derived it, the equation 13. Oh, sorry, I think it's so actually, so this is the equation 13 here, where in the former example we determined we found another expression for the ideal gas equation in terms of density, gas constant per molar mass, and then so we are using this equation now. Where we are asked to find R. So making R the source of formula, R equals pressure times molar mass over density rho times temperature. So you now slot in the values. We are given pressure as 1 atmosphere. We are given molar mass as this 32 times 10 to power minus 3. We are given density. And the temperature. We know the standard temperature, which is 273 Kelvin. So with that, we can now make R. We can now calculate for R by slotting all the values and simplifying, and that gives us R equals 8.31 joule per mole per Kelvin. We have been using this formula for R all this while. So now I have an assignment for you. You are going to solve question 1, question 4, question under exercise 13. That's this chapter. You solve question 1, question 4, question 5, question 7, question 8, and question 19. So you have to solve them. I think here are the exercises. Start from here, and then all these. So if you go through the images, the exercises, I've already snapped them. Alright, so but endeavor to get the textbook is going to help you a lot. Alright, so that's it. Let's say we are through with chapter 13 so far. Next video we will now treat other stuff. So that's it.